Next question is from 2001 under energy. Two particles A and B have equal momenta. When I'll just underline this part. This statement means they have equal momenta. So MAVA must be equal to MBVB. We can start with that. But the velocity of particle B is 4 times that of particle A. So when you say B over VA, that is 4 over 1. And moreover, from this equation, we can say um, MA over VB, it's actually equal to VB over VA. All right. So VB over VA, that is equal to 4 over 1. That is MA or MB as well. Now the question is, what is the ratio between kinetic energy of A divided by kinetic energy of B? Kinetic energy of A and kinetic energy of B, the ratio. That's easy. Half MA VA squared divided by half MB VB squared. Half and half cancels off. What is MA divided by MB? That is 4 over 1. Into what is VA squared over VB squared? Now, if VB over VA is 4 over 1, that means VA over VB is obviously 1 over 4. Therefore, VA squared over VB squared can be written as 1 over 4 squared, if not 1 over 4 squared. So 4 can be cancelled out, and final answer is 1/4. Pretty straightforward, that question. Similar to the question in year 2000. That's it, just simple stuff. A cricket ball is hit for a 6. It leaves the bat at an upward angle of 45 degrees to the horizontal with kinetic energy K. Kinetic energy of the ball at the top of its flight is, neglect air resistance. Okay, this is a question from year 2003. Now, talking about kinetic energies, this question can be approached in different ways. I will try to come up with a common equation so that we can get the answers for any question we get. So when you throw or hit a ball, you're obviously hitting it for a 6. So if you ignore air resistance, if you hit the ball at the angle theta, the ball will go like this, and then it would reach the ground, and the path will be a symmetrical path like this. If you hit the ball, if air resistance is ignored, but in reality it doesn't happen that way because air resistance is there. But this is hypothetical, so no problem. And when you hit the ball, let's say I mark the velocity as V. So at the topmost part, we know the vertical component of velocity is 0. There will be only the horizontal component of velocity, that is V cos theta. And when the object reaches the ground, again, if the air resistance is ignored, we can say that the final velocity is also V, same velocity, if air resistance is ignored. Okay. Now, at this point, initially, kinetic energy. At this point, the kinetic energy is, I'll write here, kinetic energy is equal to half mv square, and that is equal to K according to the question. Okay, initial kinetic energy is K, so I'll take it as K. And at this point, at the maximum height, we all know the kinetic energy is going to be, I'll take it as when maybe K dash or something, that is half mv cos theta whole thing square. Therefore, that is half mv squared cos square theta, and we have already defined half mv squared, that is the initial kinetic energy K, that is K cos square theta. K cos square theta. Okay, so this question is about angle being 45 degrees. They might give you angle as 30 or 60. You have to be ready. Now, when theta is 30 or 45 or 60, we can think of the values now. Cos theta. For 30, it is root 3 by 2. For 45, it is 1 over root 2. For 60, it is root 3 by, it's half actually, it's half. So what about cos square theta then? Cos square theta here will be 3 over 4. It is 1 over 2, and it is 1 over 4 if you square them. Yeah, right. So what is going to be K cos theta then? K cos square theta. K cos square theta is going to be 3K by 4. And this is K by 2, because you have just multiply K by this value. and k by 4. All right. So for this particular question, the answer is going to be k by 2, because for cos square theta, I have to substitute cos square 45. Therefore, the kinetic energy will be half. Now, if you expand this question further, if they ask you to plot the variation of kinetic energy of the object with time for different angles. Now, one, and then you can think of another one, this like this, two. If not, let's try to draw them all in the same diagram. All right. So let's start with 45 degrees itself. For 45, now time, I'll take the time of flight, will take it as t. Therefore, here it will be 0, and when the object reaches here, it will be t. And if the air resistance is ignored, exactly the time here will be t by 2. So let's use that as our reference. Here it is t. Therefore, in the middle, exactly it's t by 2. Okay, right. So as we go up, we can compare like this. And for all three situations, when you change the angle, let's say the initial velocity was same. Kinetic energy is a scalar, so the direction doesn't really matter. As long as the magnitude doesn't change, kinetic energy will not change. So all three graphs, let's say they start at the value of k, the initial velocity of the object. When the angle is 45, I'll use red color for that. When at time equal to t by 2, that means when the object reaches the maximum height, the kinetic energy was k by 2. Therefore, the graph for 45 degrees, it's going to look like this. It will bend like this because it's cos square theta, won't be a straight line, and then it will go back to k like this. Hope you all can understand. And this is for 45 degrees, when theta is 45 degrees. And when theta is 30 degrees, you can see, I'll use blue color for that. The graph is going to go like this. We start at k, and then we go up to 3k by 4, and then we go up again like this. So this value is 4. This value is going to be 3k by 4. All right. So this is for angle 30. And moreover, if you consider it for angle 60, you can see the kinetic energy at the maximum height is k by 4. Therefore, the graph will sag further move down like this. Then the graph will go. Right. So this is k by 4. I have seen these questions in model papers where they will ask you to plot this graph. They will give you graphs and they will ask, and they will give you reference lines. So the graph of 45 will be going through this middle point, but for graphs for 30 and 60 will be little different like this, because they will give you these angles because you know the values, cost values of these angles. Most probably they will be asking about these angles. Hope this is clear to everyone. Now, these were the variations for kinetic energy graphs. In case if they ask you for potential energy variation, to start with, we can take this ground as our zero potential level. Therefore, at the ground, gravitational potential energy can be considered to be 0. So here also the gravitational potential energy is going to be 0. At the maximum point, gravitational potential energy will be maximum height. All right, fine. Therefore, now we know total energy is equal to kinetic energy plus gravitational potential energy. So if kinetic energy increase, this is constant. Why is total energy constant? Because they have ignored air resistance. Their total energy is going to be constant. So when kinetic energy increases, gravitational potential will decrease in the same manner. If kinetic energy is increasing linearly, gravitational potential energy will decrease linearly. Therefore, if you plot the graph for potential energy for different angles, same case, what kind of graph can we expect? So potential energy and times t by 2 and same times, okay, t by 2 and t here. When we consider that, you have to draw upside down graphs, the opposite of that. Graph should start from 0. And first of all, let me draw the graph for 30 degrees, and the graph will be like this. Sorry, the graph will be like this. And this value now will be k by 4. This value will be k by 4, not 3, because when you add everything, it should be k. 3k by 4 kinetic energy now, potential energy is k by 4. And if you draw, this is for 30 degrees, theta is equal to 30. And if you draw for 45, then the graph will be like this. And this value is going to be k by 2. And finally, if you draw the graph for 60, then the graph will be like this. This is the graph for 60 degrees, whereas the value for potential energy at the maximum height is going to be 3k by 4. Why is that? Because initially potential energy is 0, kinetic energy is k. So the total energy is k always. Total energy should be always k. So in the middle, when time is equal to t by 2 for 30 degrees, if the kinetic energy is 3k by 4, potential energy must be k by 4. Then only when you add 3k by 4 and k by 4, the total energy will be k. All right. So we have covered both graphs for both potential energy and kinetic energy for 3 different angles. Hope this is clear, concise. Consider the following statements. This question is from 2003 once again about mechanical energy. If the kinetic energy of a particle is constant with time, its momentum should also be constant with time. Now you have to be very careful in this question. We all know that kinetic energy, it is scale. But on the other hand, momentum, it's a vector. So here direction is a must. Direction we have to consider. Direction you have to consider. Whereas for kinetic energy, direction is not an issue. All right. So let's say if kinetic energy should also be constant, that's the problem. Should, they are saying momentum should also be constant with time, and if kinetic energy is constant. Now think of a situation like this. Think of a car taking a curved road. So it is, but it's still moving at a constant speed. It can do that. It's okay, no problem. Let's say it's moving at a constant speed of v. So its kinetic energy will continuously be half mv square because its mass is m. So its kinetic energy is going to be continuously half mv square. Kinetic energy will be constant, but okay, kinetic energy is constant, speed will be constant. Speed is also a scalar, but the problem is both velocity and momentum will not be constant. Velocity and momentum not constant. What's the reason? Because the direction is changing. Direction changing does not affect scalars like kinetic energy or speed, but direction change definitely affects vectors like velocity and momentum. Therefore, this is incorrect. Should also be constant with time. We can't agree with that because this. If the momentum of a particle is constant with time, its kinetic energy should also be constant with time. All right. That is correct because now this is the explanation for statement A. Let's go to statement B. Talking about statement B, if the momentum is constant, who should be constant? Of a particle. So the mass is anyway constant of a particle. Therefore, if a particle has constant momentum, it should definitely have a constant velocity. By velocity, I mean it should move at constant speed in the same direction, or it should have the same velocity. The velocity can't change, the direction can't change, the magnitude also can't change. Okay, therefore, here what is the kinetic energy? Definitely half mv square. Here also kinetic energy is going to be half mv square because both m and v are constant for case B because momentum is constant. Therefore, B should be correct. C. If the momentum of a particle varies linearly with time, all right, C. What are they saying? Momentum of the particle is varying linearly with time. So momentum, it's equal to mv, and with time it is varying linearly like this. Now we know mass is constant. Mass is constant. Therefore, shape of the variation of momentum, it's going to be equal to the shape of velocity. So if momentum is increasing linearly, that means you should know velocity is also increasing linearly. If velocity is increasing linearly, we discussed in the previous questions, with time, kinetic energy, what about kinetic energy now? Kinetic energy is actually equal to half mv square, isn't it? Half mv square. The shape of kinetic energy graph, that is going to be definitely similar to v square, not v square. So if v is increasing like this with time, like we discussed earlier, time 1, 2, 3, just let's think of some values here. Let's say this is 1, let's say this is 2, not 1, 2, 3, let's say, let's go for 2, and then let's go 4 or 6, something like that. These numbers are not that important, right? Now, if you plot the graph for a v square, then the values will be increasing like this, is it? It will be increasing as a curve. It will bend upwards like this as a curve. Because if v increases linearly, v squared increases non-linearly. But statement says its kinetic energy should also vary linearly with time. That is incorrect, because it won't be varying linearly with time. All right. If you use these values for mv, then you should know these the values of the kinetic energy will vary non-linearly, right? Mathematically, you should be able to figure it out. If not, you can just think of numbers like this, but I think it's a waste of time. But I'll just explain it very quickly now. Let's say m is 1 kilogram. M is 1 kilogram. Or let's say, yeah, okay, m is 1 kilogram, never mind. Then if you plot the values of v squared, when m is 1 kilogram, velocity after time 1 is 2 meters per second. And if I substitute it here, the answer you will get for kinetic energy is 2. And when time is equal to 2 seconds, momentum is 4. That means since mass is 1 kilogram, velocity is 4 meters per second. Substitute that here and find the kinetic energy. Half into 1 into 4 square, and that will be 8. 2, and the next one will be 8. Right. And the next one, after 3 seconds, momentum is 6. If momentum is 6 after 3 seconds, 1 kilogram, velocity is 6. So when the velocity is 6, what is the kinetic energy? Half into 1 into 6 square. Half into 1 into 6 square is 18. Therefore, you can see the gap between the values, it keeps increasing. That's why the curve bends upwards like this. So the answer is only B correct. Therefore, second should be the most accurate answer. The next question is from 2004. Total electric power generation capacity of Sri Lanka is approximately 2.1 gigawatt. What is 2.1 gigawatt? That is 2.1 into 10 to the power 9 watt. Because giga represents 1 into 10 to the power 9. Mega represents 1 into 10 to the power 6. And kilo, simple K, represents 1 into 10 to the power 3. So in that line, giga should be 1 into 10 to the power 9. And next one is tera. That is 1 into 10 to the power 12. It goes on like that. If this power is to be generated by converting mass into energy, this is where Einstein comes. When mass is converted to energy, there is something called fission, there is something called fusion. In sun, fusion happens. Two hydrogen atoms combine to form helium, and during that time, energy is released. And in nuclear reactors or in nuclear power plants, fission happens. We will learn about this in grade 13, final lesson. Okay, there we use a uranium and we bombard it with a neutron, and then it separates to several atoms while releasing 3 more neutrons, and it releases a lot of energy. There, what happens is mass will be lost. Mass will be lost. The mass of the reactants and the mass of the products will not be same. So the lost mass is actually converted to energy. So when something like that happens, when mass is converted to energy, we use Einstein's equation, that is E equals mc square. Anyone who even who hasn't even studied physics, they all know this equation, right? Mc square, E equals mc square. So that's the equation you have to be using. But let's go to the question. How much mass per second should be converted into energy? How much mass per second should be converted into energy? And they are talking about power. Therefore, you have to divide either side by time in this equation. Energy divided by time equals to mass divided by time into c square. And remember this c, this is actually speed of light. Because you are converting mass energy to light energy. If not, you are converting mass energy to an electromagnetic wave. So we all know electromagnetic waves can travel at the speed of light. That's why this equation comes. Now, energy over time This is energy. Huh? When you divide energy by time, you will be getting power equal to mass divided by time. That is what we are supposed to find how much mass per second. So this is mass per second into c square, right? For power, you should carefully substitute 2.1 into 10 to the power 9 mass over time we have find out and multiply that by 3 into 10 to the power 8 squared. And moving on, mass over time is going to be 2.1 into 10 to the power 9 divided by 9 into 10 to the power 60. Correct? And when you divide that 2.1 by 9, I think you will be getting 0.23 by looking at the answers. I can assume that 0.23, and you have to carefully substitute. Simplify the 10 to the powers. It's 10 to the power minus 7, is it? 10 to the power minus 7, right? And that is kilograms per second, because we have substituted everything in SI units, so the answer will be in kilograms per second, right? We can eliminate the fourth and fifth because 3 is there, so it's either 1, 2, or 3. I can convert this to grams. How can I do that? I can do this. I can convert it to grams by multiplying it by 1000. Therefore, it will be 0.23 into 10 to the power minus 4 grams per second. Hope you understood it. In 1 kilogram, there is 1000 grams, so I multiply by 1000. But that in terms of kilogram per second, wrong. They have got 2.3. In terms of grams per second, it says 23. That is also wrong. In terms of grams per second, it should have been this. But I can do something like this. This can be written as 0.023 into 10 to the power minus 3 grams per second. 10 to the power minus 3 grams stands for milligram. Therefore, it can be written as 0.023 milligrams per second. So, obviously, the answer must be first. So, with your mechanics knowledge, I don't know whether you can, I don't know how far you can go there, but this part, converting energy to power and everything, it's fine. And this equation, you are supposed to know. Without this equation, you can't approach this question.